Hello virtual students. This video is going to be primarily on energy within trophic pyramids and also NPP and GPP, a crowd favorite. So, GPP, let's talk about it. Total amount of energy that plants capture and assimilate in a given period of time. Basically what that means is all of the energy it takes in for photosynthesis and is going to be able to assimilate or really turn into glucose, right, photosynthesis, over some period of time. Net primary productivity gets confused with gross primary all the time. The difference is that net is what it actually gets to turn into growth and keep. Now, there is a reason that there's a difference between these two, and it's that respiration. We mentioned this in the previous video. Respiration occurs in all living things. So there's going to be some loss of energy over a period of time, and that's what we have to take into account between all of the energy it takes in and then what it actually ends up taking, getting, and then building itself up. So NPP represents the rate at which organic material is actually incorporated into the plant tissue for growth. And so how you figure this out mathematically is you take GPP, you subtract the respiration, and you end up with NPP. And only NPP is available to food as the other organisms. So right, we're talking about plants here. So anything that it's building as tissue is going to be available for something that's an herbivore or an omnivore that feels like eating grass or whatever it is. But the point is that only the NPP is going to be the available food source. Here are a few terms that are going to help us discuss trophic pyramids and energy. So biomass. The energy in an ecosystem is measured in terms of biomass, and it is the dry weight of all organic matter of a given trophic level in a food chain or food web. So we're talking about the actual matter, right? The organic matter, what growth that plant has built. We call that biomass. And we can also say that biomass is the same thing as NPP, right? Because NPP is the growth of the plant, the actual growth, the growth that stays there and isn't lost due to any process. So if a plant is growing, that is its increase in NPP and its increase in biomass, right? It's literally getting more massive. Standing crop, the amount of biomass present in an ecosystem at a particular time. Ecological efficiency, the proportion of consumed energy that can be passed from one trophic level to another. That's definitely something you should remember from last year. There's the golden rule where 10% is the amount of energy that goes up, and that's a pretty good baseline. It's not always exactly 10. Sometimes it's plus or minus a couple percent here and there, but it's close to that. And then trophic pyramids, the representation of the distribution of biomass among trophic levels. And again, biomass is really also talking about energy, not necessarily just. So I find this image to be pretty good at explaining the difference between GPP and NPP. First off, plants are really bad at capturing light for photosynthesis. So 99% of solar energy is reflected or passes through producers without being absorbed. Wah, wah. 1% of solar energy striking producers is captured by photosynthesis. This is the GPP, right? The gross amount of photosynthesis. Then 60%, it's saying here, of GPP is lost to respiration. In this example, we'll see that some of the word problems change the percentage, but point is, GPP has a loss due to respiration. And then you end up with NPP at the end. So here it says, right, if 60 is lost, then 40% is going to support the growth and reproduction of producers, and we can also call that NPP. And again, we can also call that the addition of biomass, because again, it's growth. So growth, this energy, NPP, biomass, it's all the same thing. Just a lot of different ways of saying it. So what we care about in this slide really is just the equation, NPP equals GPP minus respiration loss. The bottom part I haven't seen used and isn't showing up in the new version of the apes CED, so we're not going to worry about it as much, but it's up there just in case you're curious. There are some word problems you could play with if you just want to do some math practice. So here is a math problem of NPP GPP, and I'm just going to do it kind of in Paint. Hopefully it looks okay, but this is a simpler type of problem, and we're just going to see how the equation works. Also, whenever you're doing a problem in apes, units are really, really important. And we always have to write our equations to make sure that we know exactly what we're doing. So before we even start, we know it's an NPP-GPP equation, so we're going to write it out. So it's oh boy, this is terrible. NPP is equal to GPP minus respiration. I'm just going to put resp. Right? So that's our equation. So now let's read the word problem, and hopefully that'll help us plug some things in. A wetland ecosystem has an NPP of 1.02 kilograms per meter squared per year. So we can write that, and we still need our units. So 1.02 kg, looks like a Y, oh boy, per meters squared years. Oh boy. Equals, and then GPP of 2.80. So 2.80. And then just to save time, I'm just going to write a scribble here, but you guys have to write your units out. If I was doing this on paper, I would definitely do it, but just to save time in the video so you're not watching me write this forever. Oh gosh, that's a huge point. So just to be clear, 1.02 kilograms per meter squared per year equals 2.80 kilograms per meter squared per year minus x. Because we don't know what the respiration is based on the question. How much carbon is being used during respiration? We don't know. So what could you do? Well, you could add x to both sides. And after you add x, you could also then, to move this over, you could subtract the 1.02 units minus 1.02 units. I gotta figure out a better way to do math, folks. But what you'll end up with is x is equivalent to that 2.80 minus 1.02, which should give you 1.78 and then units. So I'm just going to check my math just for fun. Hopefully I can do math. 2.80 minus 1.02 is 1.78. Good. And that's another thing, folks. During this test, you are going to have the ability to use a calculator. So please do so. All right, folks, we're going to do another problem. We're going to do part A to calculate the net primary productivity of the rice as part of this word problem. We're also going to skip over the efficiency because, again, it's not something that I've seen come up, but if you feel like doing it yourself, have at it. So it says in a rice paddy in Southeast Asia, the insulation energy is, 6 million calories per meter squared per day. The gross productivity of the rice is, the gross productivity. So I'm going to write that down here, 0.012, and then we'll just write this all out, grams per centimeter squared per day. And I know that it's only a 2, but it's the best I can do, folks. I'm going to need to shrink this a little bit, I think. Let's try 24. That should work. Minus resp. Okay. It says the respiration loss is 20%. How are we going to find the NPP if they gave us the GPP and then they gave us a percentage respiration? Well, I'll show you. What you do here is it's NPP is equal to GPP minus GPP times the percentage. So what you're going to want to do for this is NPP equals 0.012, and I won't write out all the units because saving time, but please do, again, please, well, you know what, I'll just copy and paste. can't do that on the test. But minus, then we have 20%. So we have to put GPP, right? To get 20%, we have to multiply the GPP by something that would give us 20% of it. So we can write 0.012 grams. Well, I've got my units here. I might need to shrink it again. And then we need to multiply that by, to get 20% of something, you can multiply it by 0.2. So now we have the GPP that they gave us in the question, and now we are finding, if we take away 20% of it by multiplying it by 0.2, we would find the NPP. So go ahead and do that. All right. So hopefully you pause the video here and come back. And now you've restarted the video. Good. So your answer should be, if you multiply this out, it should be NPP is equal to 0.012. Put your units minus. Now when you multiply those, you get 0.0024. And we can put the units. And then your NPP will be equal to 0.0096. So that is how you figure out if they give you the respiration, not as a flat amount, but as a percentage. So why do we care about NPP? Well, it tells us about areas that have a lot of growth, and places that are teeming with growth have a lot of energy, have a lot that they can provide because they probably have a lot of different organisms that they support. Places that have a lot of NPP are, in terrestrial ecosystems, swamps and marshes as the number 1, followed by tropical rainforests as number 2. And that might be a little bit stunning, right? You might think tropical rainforest has to hands down be the biggest one, but swamps and marshes have a lot going on. If you think about a swamp and or a marsh, it's green everywhere. There's all sorts of different growth, things growing on trees, moss everywhere, even some kind of pond scum or lily pads, frogs, snakes, alligators. You could think of so many different things in that area. It is densely packed with life. Same thing goes for estuaries. Estuaries are the areas where a river opens up into a larger body of water, usually the ocean, and you get these kind of cool mixes of salt water and fresh water, and there's a lot of very strange creatures that live there. I don't know if you've ever seen like fiddler crabs with the one big hook claw, and they kind of mate by doing a whole bunch of hand waving. I don't know, there's cool things that live there, but the point is that these are some of the places that have just like crazy amount of NPP because of the different plant life that lives there, and therefore they support a whole bunch of different organisms. This brings us to our ecological pyramids. So these are going to represent the energy within the different trophic levels that we were talking about before. And we have 3 main types. We've got a pyramid of numbers, a pyramid of biomass, pyramid of energy. And again, this is all talking about the energy that's within the levels and also the loss that occurs as heat. So in a pyramid of numbers, it illustrates the number of organisms at each level. So here you can see that there are 10,000 blades of grass. In this area, there are 10 of the primary consumer of the field mouse, and there is 1 secondary consumer, which is the bird of prey. This is showing that there are less as you go up of every single organism, right? There's just way less birds and way less mice than there are blades of grass, but it does not indicate anything about biomass or the amount of energy transferred. It is simply just the numbers, the raw numbers of what organisms are in this area according to the different things we're looking at in this food chain. The next one is a pyramid of biomass. So this one has the pyramid based not on the number of individuals, but it is the actual amount of living material that each of these different things takes up. So it, as you can see on the side, is 10,000. Now we're not talking blades of grass, we're talking grams per meter squared. And then it's followed by 1,000 of the grasshoppers, 100 grams per meter squared of the toads, and 10 grams per meter squared of the snakes. So we're not looking at 10 snakes, 100 toads. No. We're looking at the actual biomass of these different categories. And then if we wanted to get very technical with energy, we could actually have the exact amount of energy that is within each of these different trophic levels. Here we're looking at kilocalories per meter squared per year. And again, it's a food chain with producers, primary consumers, secondary consumers. We're just talking about energy instead of talking about the numbers of the biomass. It's good to notice that there are these different kinds of pyramids, because if you get a question and you jump to conclusions that you think they're all the same, you might get caught off guard by a biomass pyramid when you were thinking that it's one looking at numbers, like we were looking at with the snake and the frog in the previous slide. So definitely be careful and read your unit. So finally we get to the rule of 10, right? The energy flow pyramid, where we see each of the different levels going up from the producers to the primary consumer to the secondary consumer and the tertiary. They are all losing that 90% to heat, and that is going to also then reduce it so that it is only 10% of what it had before. And this is talking about the usable energy available. So it's the actual energy that is available to each, and they only pass on approximately 10%. But like we said in nature, nothing is perfect. It's an approximation.